All right, so here we are in Chapter 5. Chapter 5, we're only going to be working through the first two sections. 5.1 deals with eigenvalues and eigenvectors. If you have been through a course in differential equations, an introductory course in DE, you will have encountered these before. They show up when you are taught how to solve systems of linear differential equations. But whether you've heard of them or not, we're going to be learning about those here. So let's start with the definition of eigenvalue and eigenvector. So if we have a square matrix, A is going to be an n by n matrix in this case, and X is going to be a vector in Rn, which we're going to be thinking of as a column vector typically. We say that X is an eigenvector of A if Ax is equal to lambda x for some scalar lambda. If we can find such an x and such a lambda that do this, then we say that x is an eigenvalue of A, and lambda is an eigenvalue of A, and x is an eigenvector corresponding to that eigenvalue lambda. Your book doesn't use this terminology, but this terminology is really prevalent in other books, and it's useful to have this. If we can find an eigenvalue and an eigenvector that go with it, together we refer to those as an eigenpair. And if you take more courses in linear algebra, there's all sorts of eigen things out there. There's eigenfunctions. We're going to talk about eigenspaces a little bit later. That prefix shows up in a lot of different related concepts. But I want to talk about this definition for a second in sort of an intuitive way. So again, remember X is a vector in Rn. Basically what this says is that if you have a matrix A and can find an eigenvector X, then multiplying A to X like this effectively just scales that vector. We know that when you multiply a vector in Rn by a scalar like lambda, then essentially what that does, and I have a diagram here to show it, is it takes that vector x and maintains the same direction if lambda is positive, but scales it by a factor of lambda. So for example, if lambda equals 2, it would double the length of that vector but not change its direction. If lambda was a negative value, then it would reflect that and change the direction by a 180-degree angle pointing the opposite direction. And then scale it according to the absolute value of lambda. But the point here is that eigenvectors are special vectors that go with matrices, specific matrices, such that this product has this effect on that vector. It just scales it. The same thing as multiplying it by a scalar. Okay, now let's go up here. So here's an example. I want to show that this vector 4, 5 is an eigenvector of A, and that its corresponding eigenvalue is lambda equals 2. So I'm going to basically verify both sides of this equation. So let me start with Ax. So A times x looks like 7, -4, 5, -2 times the vector 4, 5. Okay? If I were to carry out this multiplication, what we would see as a result is the vector 8, 10. Okay, and you can check the steps there to make sure that came out right. But if you notice, multiplying the vector 4, 5 by this matrix effectively just accomplished the same thing as multiplying this vector by the scalar 2. I doubled the values of those entries. So 2x, or 2 times 4, 5, gives me the same thing, 8, 10. This shows that Ax is equal to 2x. 2 would be the eigenvalue here. Okay? One thing I want to point out as well, there's no such thing as a vector that's simply an eigenvector. I can't just say 4, 5 is an eigenvector. It's relative to a matrix. I can say that 4, 5 is an eigenvector of this matrix, but it doesn't make any sense for something to simply just be an eigenvector by itself. Same thing with the term eigenvalue. There's no such thing as just an eigenvalue. It's always relative to a matrix. Okay, so this is an example where I provided the eigenvector and the corresponding eigenvalue for you. But how do you come up with these if all you're given is the matrix? Well, that's this next section down here. We want to talk about how to compute eigenvalues for some square matrix. And again, this only applies to square matrices. Matrices that are not square don't have eigenvectors or eigenvalues. So I'm going to kind of walk you through this little explanation here. But again, here's our definition, or here's the equation that gives us the definition of an eigenvector of A. So again, if x is an eigenvalue of A corresponding to the eigenvalue lambda, then we have AX equals lambda x. Now notice, if I were to subtract AX from both sides, another way of writing this exact same thing is lambda x minus AX equals the zero vector. And that would be the zero vector in Rn if A is an n by n matrix. This left-hand side, I have a common factor of x, which I want to factor that out, but I have to be careful because I have to remember that this A here is an n by n matrix, and this lambda here is a scalar. If I factor that x out by itself, it would look like lambda minus a scalar minus a square matrix, and that's not an operation that's defined for us. We can only subtract matrices from other matrices. So I'm going to change the look of this term right here. Notice that lambda x is the same thing as lambda ix, I being the n by n identity matrix. We know that the identity matrix times x would just be x anyway, so there's no difference between these two. But writing it this way, if I were to replace lambda x here with lambda ix, then if I factored the x out, I would be left with lambda I, which is an n by n matrix. That leads me to this. So factoring the x out, making that replacement, I get lambda I minus a, which is an n by n matrix. That's an n by n minus an n by n, times the vector x is equal to the zero vector. Okay? Now, writing it in this form is representing this as the matrix form as a homogeneous linear system. Again, this is a matrix times x equals the zero vector. That's what the matrix form for a homogeneous linear system looks like. So with that said, if I'm looking for eigenvectors for A, then what I'm trying to do is look for solutions to this system. Now, one thing I do want to point out, and this is really important, I don't know if I emphasize this up here, but the definition of an eigenvector requires it to be a non-zero vector. And that's just a matter of definition. So if I come back down here, I know clearly that the zero vector, is a solution to this. That would be the trivial solution. So if we have any hope of finding eigenvectors from this equation, what that would mean is that we're looking for non-trivial solutions to this homogeneous linear system. From our equivalence theorem, we know that if this matrix, lambda I minus a, if that's an invertible matrix, then this system would have only the only the trivial solution. That goes back to our equivalence theorem. So if we are to have any hope of getting eigenvectors as solutions to this, by that logic, this matrix would have to be non-invertible, or we could say that it's singular. But to say that this is singular, again, by our equivalence theorem, would be the same thing as saying that its determinant is zero, which is what we have here. So I will get solutions, non-zero solutions to this linear system as long as the determinant of that matrix is not equal, or is equal to zero. Notice now, A is a matrix that we would have been given in the first place. I is a specific matrix, it's the n by n identity matrix. The only real unknown in this thing is that lambda. So what this equation does for us is it gives us a means of solving for lambda, determining what the possible eigenvalues of this matrix are. So because this equation, determinant of lambda I minus a equals 0, and this is the scalar 0 because it's the result of a determinant, Because this is how we determine eigenvalues for a matrix, it's an important equation in this chapter. We call it the characteristic equation of A. Okay, so let's run through an example showing how we would find eigenvalues, just eigenvalues for now. We're not going to worry about the eigenvectors quite yet, but eigenvalues of this matrix A. Okay, so first thing I would want to do is determine the characteristic equation of A. Now remember, the characteristic equation is the determinant of lambda I minus A. So I'm going to begin by finding lambda I minus A, which would be equal to this. Notice this is I in this case would be the 3 by 3 identity matrix, and if I multiply it by the scalar lambda, that's going to look like this: lambda 0 0 0 lambda 0 0 0 lambda right there, minus our matrix A, which is 1 negative 3 3 3 negative 5 3 6 negative 6 4. Okay, if we subtract that, we're going to get lambda minus 1, positive 3, negative 3, negative 3, lambda plus 5, negative 3, negative 6, positive 6, lambda minus 4. Okay. My characteristic equation is what I get if I take the determinant of this, so the determinant of this matrix, and set it equal to 0. So again, we want the determinant of lambda I minus A, which is this determinant right here, lambda minus 1, 3, negative 3, negative 3, lambda plus 5, negative 3, negative 6, 6, lambda minus 4. We're going to set this equal to 0, but let's start by doing a cofactor expansion for this. So I'm going to expand this along the first row. So I'm going to have lambda minus 1 times the determinant lambda plus 5, negative 3, 6, I don't need parentheses there. I don't know why I'm doing that. Lambda minus 4. Okay. Remember, we have a plus minus plus pattern, so this is going to be minus 3 times the 2 by 2, negative 3, negative 3, negative 6, lambda minus 4, minus 3 times negative 3, lambda plus 5, we're negative 6, 6. Okay. Now this, if I expanded all of this out, and then I'd end up with kind of a big long algebraic looking expression. If I simplified it completely down, you're going to see that the result looks like a polynomial in the unknown lambda. So in this case, the polynomial ends up reducing down to lambda cubed minus 12 lambda minus 16. Okay? We want to set that equal to 0. This is my characteristic equation that I want to try and solve. So to solve this, normally you would attempt factoring. Now this is a cubic polynomial, and it might have been a while for you since you've last had to try factoring one of these. But the trick here is to use something called the rational root theorem. We talk about that in pre-calculus. Basically, we want to check and see if this thing has any roots that are rational numbers. They're going to look like factors of 16 over factors of my leading coefficient, which is 1. In other words, we're just looking at factors of 16, and we check them using synthetic division. So I'm not going to go through a whole lesson on the rational root theorem since that's a prerequisite, but maybe you'll remember this. So I'm going to pick a factor of 16. One of the ones that I know happens to work is the factor 4. If I write out the coefficients here, 1 for my lambda cubed, 0 for lambda squared, negative 12, and negative 16. then what I'm going to do is do synthetic division. 4 times 1, 4 times 4, 4 times 4, 16, it gives me 0. The fact that I have a 0 here means that this thing has a factor of lambda minus this number, lambda minus 4. So lambda minus 4 times, now the coefficients here give me the quotient. So that would be lambda plus 4 lambda plus 4 equals 0. That, however, factors down this way. Lambda plus 2 squared equals 0. And this is just solving a polynomial. I can find my zeros from here. Lambda will equal 4 or negative 2. Those are the two eigenvalues for that matrix up there. So to conclude this video, and we have more to talk about in this section, but I want to call attention to what happened here. The characteristic equation ended up giving us a polynomial, a specific type of polynomial, something that we call a monic polynomial, which means its leading coefficient is 1. We ended up with a monic polynomial equal to 0. So finding the eigenvalues of this matrix reduced down to solving a polynomial equation. That's going to happen in every example that you do. For any matrix, any n by n matrix, the characteristic equation for that matrix will always look like an nth degree polynomial. It'll be monic, meaning it has a leading coefficient of 1, and then it'll be set equal to 0. The polynomial that shows up on the left-hand side of this characteristic equation is called the characteristic polynomial of A. And again, we can confirm that here. Notice we were dealing with a 3 by 3 matrix, and what I ended up with was a monic third degree characteristic polynomial. So if you haven't solved kind of big polynomial equations in a while like this, using the rational root theorem or other techniques, this is the time when you really need that. We'll do more with this idea in the next video.